All right, everyone. Today we're going to dive into one of the most elegant, most beautifully orchestrated systems in the entire human body, the electrical conduction of the heart. For every single beat, a really precise sequence of events has to unfold, turning this tiny electrical spark into the powerful contraction that keeps us all alive. So here's our game plan. We're going to follow the journey of a single heartbeat, right from the initial spark to that final powerful squeeze. We'll start with the basic layout, find out where the electricity comes from, trace its path, see how it makes the muscle move, and finally, how the whole thing is controlled. Okay, first things first, we have to get our bearings with the basic anatomy. Because the big question we need to answer is, how does this four-chambered pump get the perfectly coordinated signal it needs to work? So you've got the atria up top. Think of them as the primer pumps. They just receive the blood and give it a little push. And then you have the ventricles down below. These are the real workhorses, the power pumps that send blood out to the lungs and the rest of the body. But here's the key. It's all about the timing. The atria have to finish their job just before the ventricles begin theirs. So that brings up the question, where does this perfectly timed signal even come from? Well, the whole process kicks off in a tiny little clump of specialized cells that act as the heart's own natural conductor, its very own metronome. And here it is, the sinoatrial node, or as we all call it, the SA node. It's tucked away up in the right atrium. You really can think of it as the conductor of an orchestra. It sets the tempo, the rhythm for the entire heart, usually somewhere between 60 and 100 beats per minute when you're just resting. Now, okay, this graph might look a little intense, but stick with me because it shows exactly why the SA node is so special. See that green line? Unlike a normal muscle cell that just sits there waiting for a signal, these SA node cells are different. They have what's called a funny current that makes their electrical charge naturally drift upwards. And once it hits a certain threshold, bam! It fires an electrical signal all on its own. It doesn't need to be told. That automaticity is what makes it the pacemaker. Okay, so the spark is lit. Now what? Where does that electrical signal go? Well, it doesn't just spread out randomly. It follows a very specific, high-speed pathway, and that's absolutely critical for getting a coordinated contraction. So the very first thing that happens is the impulse just sweeps across both atria almost like a wave, causing them to contract together. Now, this is important clinically. That electrical event is what creates the P wave that you see on an EKG. It's literally the electrical signature of the atria squeezing. But then, something really crucial happens. The signal doesn't just barrel straight down into the ventricles. Nope. It hits a traffic light. It gets to the atrioventricular node, the AV node, and it's forced to slow down. So the big question is, why? Why is this pause so vital? And the how is just brilliant. It's built right into the structure of the cells. If you look at the AV node under a microscope, its cells have fewer gap junctions. You can think of gap junctions as these tiny electrical tunnels between cells. Fewer tunnels means slower travel. So this structure acts as a natural brake, slowing that impulse down for just a fraction of a second. And that brings us to the why. That tiny delay is everything. It gives the atria just enough time to finish squeezing and top off the ventricles with blood. Without that pause, the ventricles would contract before they were full, which would make the heart a pretty lousy pump. It's an incredible piece of biological engineering. All right, so after that perfectly calculated pause, the traffic light turns green. The signal hits the superhighway of the heart, the bundle of His and all these branching Purkinje fibers. These things are built for speed. They conduct the impulse like 4 times faster than other heart tissue, getting the signal to all parts of the ventricles at almost the exact same time. So we've followed the electrical signal, the excitation, all the way down. But now we get to the main event, the climax of the story. How do we turn that electrical message into a powerful physical squeeze? That's contraction. This whole process has a name, excitation-contraction coupling, and it's just a beautiful chain reaction. The electrical signal hits the muscle cell and opens up these things called L-type calcium channels. Now, just a little trickle of calcium comes in from the outside, but that trickle acts like a key. It unlocks the massive calcium storage tanks inside the cell, and whoosh, a huge flood of calcium is released. And it's that flood of calcium that powers the actual muscle contraction. Of course, after the big squeeze, you've got to reset. The muscle can't stay contracted forever. The cells have to repolarize, which is really just a fancy way of saying they reset their electrical charge. The calcium gets pumped back into storage, the muscle fibers let go, and the heart relaxes. And that completes the cycle, getting the ventricles all set and ready for the very next beat. Now, the heart's internal pacemaker is incredible, but it's not working in a vacuum. I mean, think about it. The heart has to adjust constantly to what your body needs, whether you're fast asleep or sprinting for a bus. And that's where your autonomic nervous system comes in. It's got these two branches that act like a gas pedal and a brake for the heart, and they plug right into the SA and AV nodes to control the show. So you've got your sympathetic system, that's your fight or flight response. It's the gas pedal. It speeds up the heart rate, makes it squeeze harder, and shortens that delay at the AV node. Then you've got the parasympathetic system. That's your rest and digest mode. It's the brake. It slows the heart rate down and increases the AV node delay to conserve energy. It's a constant balancing act between the two. So why? Why have we spent all this time tracing the path of one single heartbeat? Well, here's the bottom line. You absolutely cannot understand what goes wrong in disease until you have mastered what normal looks like. Every single step we just talked about, that atrial squeeze, that AV node delay, the big ventricular squeeze, it's all measured on an EKG. And as this quote really highlights, when those time intervals are off, that's not just some academic curiosity. That's a direct sign of underlying disease. It's a major red flag for cardiovascular risk. This framework is the key to everything in cardiac electrophysiology. When you hear about atrial fibrillation, that's just chaotic signals bombarding the AV node. A heart block? That's a problem with conduction right at that AV node we talked about. It all comes back to a disruption somewhere along this elegant pathway we've just laid out. And that's what I want you to take away from this. Let me leave you with a clinical question to chew on. Now that you know the whole pathway, what would happen if you gave a patient a drug that blocks those L-type calcium channels we talked about? Where in this sequence, from the AV node's delay to that final ventricular squeeze, would you expect to see an effect? If you can answer that, you're already thinking like a cardiologist because you're laying the foundation for understanding cardiovascular pharmacology.